Somewhere between you and the nearest star, astronomy pulled a quiet prank on the rest of us. Instead of measuring the cosmos in light years the way documentaries and news articles always do, professionals use a unit that sounds invented and feels totally backwards. The parsec does not mark a special boundary in space, nothing magical happens at one of them, and almost no star sits at exactly that distance. Yet if you open research on galaxies, dark energy, exoplanets, black holes, you will drown in parsecs, kiloparsecs, megaparsecs. Tonight we are going to find out how that happened, and what this strange choice reveals about how science really works as a human project. If you enjoy journeys that mix cosmic scale with human messiness, tap like, subscribe and come along into the dark. If you have ever tried to follow real astronomy papers, you have probably felt the whiplash. On television, Andromeda is about 2.5 million light-years away. The Milky Way is about 100,000 light-years across. The nearest star is just over 4 light-years from the Sun. Those numbers feel intuitive. Light is fast, a year is familiar, light-year is obviously huge. Then you peek at the professional literature, and suddenly Andromeda is 780 kiloparsecs away, the galactic center is about 8 kiloparsecs away, and your brain quietly checks out. The light year tells a story all by itself. You hear that a galaxy is 10 billion light-years away, and you immediately know you're seeing it as it was 10 billion years in the past, when the universe was young and our planet did not yet exist. Time and distance fuse in a way that makes emotional sense. The name is almost a tiny science fiction short story on its own. No extra explanation required. The unit carries its own poetry, the parsec does the opposite. To understand it, you need several layers of background. You need to know that Earth orbits the Sun and that we use that orbit as a gigantic baseline, a cosmic version of the distance between your eyes. You need to know how astronomers measure tiny angles on the sky, down to 1 second of arc, a slice of a degree so small that a human hair at city block distance would barely match it. Then you tie those together into a triangle and define a distance where that 1 astronomical unit base appears under a 1 arc second angle. That distance is 1 parsec. Nothing explodes there, nothing changes state there, it is just where the geometry works out neatly. From the outside, this sounds ridiculous. Why would a serious science choose a distance unit that depends on how Babylonian mathematicians chopped up a circle into degrees and then into minutes and seconds? Why not use something clean like light travel time or a round number of kilometers? Why hold the entire universe hostage to a human choice about angle subdivisions made thousands of years ago? It feels like discovering that all cosmology secretly depends on the number of slices someone once cut a pie into. Inside astronomy, though, the parsec solves a very specific pain. For the people who first tried to measure star distances, the hardest part was not philosophy, it was arithmetic. Picture sitting under a dim oil lamp in the 1800s, leafing through notebooks full of star positions, doing trigonometry by hand with printed logarithm tables. If the parallax angle you carefully measured is half an arc second, the distance is 2 parsecs. If it is a quarter of an arc second, the distance is 4 parsecs. If it is 1/100th of an arc second, the distance is 100 parsecs. 1 over the angle, that is all. No giant conversion factors, no endless zeros. That is the hidden power here. You trade intuitive meaning for brutal efficiency. A unit that makes no sense to your gut makes perfect sense to your tired brain when you have to process hundreds of measurements. And once enough people build their careers, their data tables, their catalogs, and eventually their computer code around that convenience, changing becomes harder than just putting up with the weirdness. The parsec stops being a clever hack and starts being the language of the field. There is another twist. That obscure triangle is not some side alley of astronomy. It sits at the base of the whole cosmic distance ladder. When we say a Cepheid variable star in another galaxy has a known true brightness, that calibration traces back to a few nearby Cepheids whose distances were first measured in parsecs using parallax. When we say a Type 1 supernova lets us gauge distances of billions of parsecs, its brightness scale ultimately leans on those same local anchors. Even the famous Hubble constant, the number that tells us how quickly space itself expands, is usually written in kilometers per second per megaparsec. This odd unit is baked into the equations that describe the growth of the universe, and the story is still evolving. In the 21st century, the Gaia satellite turned parallax from a heroic 1 star at a time marathon into industrial-scale cartography. Gaia measures positions and parallaxes for more than 1 billion stars with mind-bending precision, down to micro-arc seconds for the brightest ones. Its raw data are angles in arc seconds. Every distance in its catalogue is a simple one divided by parallax, poured out directly in parsecs. The biggest star map in human history is built out of this unit that almost nobody outside the field can picture. That choice will shape astronomy for decades, simply because so much infrastructure now rests on it. So when we ask why we use parsecs, we are not just asking about a quirky unit. We are digging into how scientific standards take root, how convenience and history can matter just as much as deep principle, and how hard it is to change course once enough work has been done in one particular language. We are also asking what we might lose by hiding the light year from professional work and what we might gain if software could translate units as easily as it translates languages. In the next parts, we will rewind to the era when the stars were nailed to a crystal sphere, follow the stubborn people who tried to make them move on paper, watch Friedrich Bessel squeeze an impossible angle out of noisy data, see how that geometry grew prefixes and climbed from stars to galaxies, and then step into the modern world of Gaia, gravitational waves and cosmic tension over the true expansion rate. Along the way, the parsec will turn from a random jargon word into a surprisingly revealing clue about how science grows. Picture yourself on a hill 2,000 years ago with no streetlights, no planes, no satellites creeping across the sky. The night is a black dome punched full of cold white points. Night after night you look up and you notice something very simple and very persuasive. Almost everything is locked in place. The same patterns rise in the east, swing overhead, and sink in the west, with a regularity that feels almost mechanical. The ancient Greek astronomers were not naive. They noticed the odd ones that wandered, the bright points we now call planets that drifted slowly against the background patterns. Mars looped and backtracked. Jupiter and Saturn crawled along the zodiac. These were the troublemakers. But the stars themselves seemed different. They kept formations perfectly. Orion never stretched. The Big Dipper never sagged. No star crept away from its neighbours in any human lifetime. If you're trying to build a model of the universe from that evidence, the simplest story is that the stars are not scattered in depth at all. They are all mounted on a single surface at the same distance. The Greeks gave this surface a name, the sphere of fixed stars, and imagined it as a kind of crystalline shell surrounding the planets. Hipparchus, around 30 BC, catalogued more than 1,000 stars with painstaking care, recording positions and brightness. He saw the same illusion we would see under that sky in a flat pattern, painted on a distant dome. Aristotle pushed this into full-blown philosophy. He divided the cosmos into two regions. Below the orbit of the moon was the realm of change. Air, water, earth and fire, where things decayed, burned, broke and died. Above the moon was the realm of perfection, a fifth element he called ether, pure and eternal. The stars were part of that perfect realm, glued into an invisible sphere of this fifth substance. They could circle around Earth, but they themselves never changed, because perfection does not twitch or flicker. It is easy now to roll our eyes at crystal spheres, but within the limits of the data, it was a brilliant compression of the sky into a single idea. Every observation a Greek astronomer could make with naked eyes supported it. Over centuries, the constellations held their shapes. No nearby star detached and slid across the sky. Nothing in naked eye observations hinted at depth or three-dimensional structure. They had no reason to think that one star in Orion might be hundreds of times farther away than another. The key missing ingredient was the tiny effect we now call parallax. Your brain uses it constantly. Your two eyes see slightly different views, and that discrepancy lets you judge distance. Hold a finger at arm's length, wink one eye and then the other, and you see the finger jump against the distant background. That jump is parallax. If the effect had been large for the stars, the Greeks would have spotted it. But the earthly baseline between two eyes, or even between two observers on different parts of the Earth, is far too small to reveal any jump at stellar distances. So the Greeks faced a simple fork in their reasoning. Either the Earth is moving and the stars are incredibly far away, so far that parallax is too small to see, or the Earth is stationary and the stars sit on a nearby sphere. With no way to measure a shift and a strong cultural preference for a central, unmoving Earth, they chose the second path. Not out of ignorance, but because everything they could actually measure pointed that way. When later thinkers like Ptolemy refined the model, they made it even more intricate but kept that crystal sky intact. Epicycles and deferents were invented to handle the looping paths of planets. all while the fixed stars rode along on the outside. The whole structure became a grand clockwork. Earth in the middle, nested spheres carrying the moon, the sun, the planets, and finally the starry shell. It was elegant, predictive, and emotionally satisfying. You lived at the calm centre of a finite universe. Notice what this did to the idea of distance. Once you decide all stars are on the same shell, distance stops being a question you can even ask. You can talk about angular separation. You can say that two stars are a certain number of degrees apart on the dome. You can rank brightness. You can group stars into constellations and build myths on top of them. But actual depth, how far away in kilometres, becomes meaningless, like asking how thick a rainbow is. The model quietly deletes the concept. This worldview lasted not because people refused to think, but because instruments refused to help. For most of human history, the best angular measurements came from sighting tubes, careful sight lines, and human hands. You could measure the sun's path, you could track planetary loops, you could predict eclipses, but you could not tell whether a star had shifted by a fraction of an arc-second. The universe felt tidy and sealed because our tools were too blunt to crack it open. Even after telescopes appeared, the illusion of fixed stars remained powerful. Early lenses were full of defects. Mounts wobbled, buildings flexed. The tiny differences in star positions that screamed distance were still drowned in mechanical noise and atmospheric blur. Galileo could see that the Milky Way was made of countless stars, which already hinted at depth, but he still could not measure how far any of them were. The crystal sphere was starting to look crowded and fuzzy, but it had not shattered yet. From our vantage point, knowing that stars are scattered through a vast galaxy, it is tempting to treat that ancient firmament as a childish picture. Yet everything about it rests on one brutally stubborn fact. For 2,000 years, the stars did not appear to move relative to each other in any way that human senses and early tools could detect. They looked fixed because the universe is so large that our first rulers were laughably small. The sky's apparent perfection was a feature of limited resolution, not of reality. The moment the story changes is the moment someone decides to take that illusion personally. Instead of accepting the crystalline shell, they decide the fixed patterns must hide tiny motions just below the threshold of vision. They ask a dangerous question. What if the stars do move, but so slightly that only the most obsessive measurements will reveal it? In the next part, we'll meet the people who built those measurements, amplified Earth's motion into a cosmic ruler, and turned that ancient dome of fixed stars into a three-dimensional space where distance finally meant something real. To crack the crystal sphere, you need a trick that turns motion into depth. The idea sounds almost childishly simple. If you can look at something from two different positions and see it shift against the background, you can work out how far away it is. Your brain does this every moment with your two eyes. Astronomers just had to supersize the baseline from a few centimeters between eyeballs to something truly cosmic. That something turned out to be Earth's entire orbit around the Sun. By the 1600s, people like Kepler had already shown that Earth is not sitting still under a rotating sky. It is looping around the Sun once per year in a nearly circular path. By watching Venus crawl across the Sun's face as seen from different places on Earth, astronomers could estimate the size of that orbit. The diameter they came up with was around 300 million kilometers. In other words, in January Earth is on one side of the Sun, and in July it is on the opposite side, separated by that enormous distance. Now put that into the parallax picture. Imagine a nearby star sitting out in space and a background wall of extremely distant stars far beyond it. In January, you measure the nearby star's position on that wall. 6 months later, you do it again from the other side of Earth's orbit. If the star is even moderately close, its apparent position should shift by a tiny amount against the distant background. Draw the triangle in your mind. One corner is Earth in January, another corner is Earth in July, the third corner is the star. The base is Earth's orbital diameter. The angle at the star is the parallax. On paper, this is just school geometry. If you know the length of the base and the angle at the star, you can calculate the other sides of the triangle. In reality, the angle you're trying to measure is absurdly small. For the nearest stars, the total wiggle over 6 months is on the order of an arc-second or less. To feel how small that is, first split a circle into 360 degrees. Take 1 degree and split it into 60 minutes. Take 1 minute and split it again into 60 seconds. One of those tiny pieces is 1 arc-second. It is the angle a tennis ball would make if you held it about a kilometre away. 17th century telescopes were not built for that kind of finesse. Lenses flexed, mounts creaked, buildings shifted on their foundations. Turbulence in the air blurred star images by several arc-seconds, more than the signal itself. Even an astronomer's pulse, transmitted through the structure while they leaned at the eyepiece, could nudge the instrument enough to swamp the effect they were hunting. They knew in principle that the method should work, but in practice the stars refused to move. Robert Hooke was one of the first to really go after stellar parallax with serious intent. He was no amateur. He worked on elasticity, optics, planetary motion, and helped rebuild London after the Great Fire. In the 1660s, he designed a special telescope fixed high in a building so it would suffer less atmospheric distortion near the ground. His target was a bright star in Draco that we now call Gamma Draconis, which passes almost overhead in London and is therefore seen through a relatively thin slice of atmosphere. It was a clever choice. Hooke observed night after night, measuring the star's position against reference marks and convincing himself that he saw a tiny shift. He announced that he had finally measured stellar parallax. History did not agree. What he had actually detected was a different effect quietly mixed into his data. It was not the star moving because of Earth's position changing. It was the apparent position changing because of Earth's motion through space while light took time to travel down the telescope tube. James Bradley later untangled this in the 1720s and gave it a name: stellar aberration. Light does not arrive instantly. It travels at about 300,000 kilometers every second. Earth is also moving at about 30 kilometers every second along its orbit. When you point a telescope at a star, you have to tilt it slightly into the direction of Earth's motion so that the starlight can reach the eyepiece even as the telescope is sliding sideways. It is like running through vertical rain with an umbrella. Even though the drops fall straight down, you have to angle the umbrella forward. Aberration shifts every star in the sky in the same general pattern and by about 20 arc-seconds at most. It is a real effect, and Bradley's discovery was a triumph. It confirmed both Earth's motion and the finite speed of light. But it was not parallax. Parallax would move nearby stars differently from distant ones. Aberration marched them all together. For people obsessed with stellar distances, it was both exciting and infuriating. They had found something, but not the thing that they had been chasing for decades. Others took different approaches. William Herschel, who discovered Uranus and mapped the Milky Way, tried to use double stars. If two stars appear close together, but one is much farther than the other, then as Earth orbits, the nearer one should show parallax against the more distant partner. Herschel measured thousands of such pairs with heroic patience. He did not get parallax out of it, but he accidentally discovered that many of those pairs are physical binaries, stars orbiting each other under gravity. That turned into a new tool for weighing stars. Failure in one quest seeded success in another. By the early 1800s, measuring stellar parallax had become the holy grail of positional astronomy. Everyone agreed it must exist. Everyone agreed that measuring it would finally break the illusion of the crystal sphere and put actual numbers on stellar distances. Dozens of astronomers across Europe tried, claimed detections, and were contradicted by others. The reported distances jumped wildly from one paper to another, a clear sign that the measurements were not yet reliable. The underlying concept was sound. Use Earth's orbit as a ruler 26 million times longer than the space between your eyes. Watch a star very carefully for a year. Track its tiny loop on the sky as Earth moves. Convert that wobble into distance with trigonometry. But practice lagged far behind theory. Before anyone could turn that triangle into a standard tool, someone had to figure out how to push telescopes, buildings, and atmosphere into a regime where a single arc-second was not a blur but a measurable angle. That someone would be Friedrich Wilhelm Bessel, a man who treated every possible source of error as a personal insult. In the next part, we will follow him into the observatory, watch him turn parallax from an elusive rumour into a crisp number, and see how his success quietly seeds the definition of one of the strangest distance units in science. Friedrich Wilhelm Bessel did not look like the hero who would finally make the stars move. He was not born into a dynasty of astronomers. He did not grow up under observatory domes. He started as an accountant in a trading company, a young clerk whose job was to keep numbers straight in ledgers about cargo and money. What he did have was a mind that could not leave a calculation alone once it had its hooks in him. In his spare time, he taught himself mathematics and navigation, the art of finding position from the sky, and astronomy quietly pulled him away from commerce. At 20, he did something outrageous for a hobbyist. He reconstructed the orbit of Halley's Comet from old observations, grinding through tedious calculations by hand. A professional astronomer, Heinrich Olbers, saw the work and realized this was not ordinary talent. He helped Bessel get a position at a small observatory, and before long Bessel was put in charge of a new one at Königsberg. The former bookkeeper was now a director, with a telescope and a building and an entire sky to measure. What set Bessel apart was not only skill, but attitude. Many astronomers of his time treated instruments with a kind of gentlemanly trust. You point the telescope, you read off the scale, you write down the value. Bessel treated every instrument like a suspect. If a reading could be wrong, he wanted to know how and by how much. He worried about atmospheric refraction bending starlight differently on cold nights and warm nights. He worried about metal tubes expanding and contracting. He worried about wind pushing on domes and foundations shifting with seasons, so he measured those things too. He attached thermometers to his telescope and watched how its length changed as temperature drifted. He recorded barometric pressure and humidity so he could correct for air refraction. He studied the mechanical play in the mount, how gravity flexed the tube as it pointed in different directions, effects that most people shrugged off as background noise became parameters in Bessel's personal error budget. Before he even aimed at a star, he was already building a model of everything that could go wrong with the measurement. By the late 1830s, parallax had become the unsolved boss battle of astronomy. Many had tried and failed. Some had even claimed success only to be contradicted by others. Bessel decided it was time to attack the problem with the full weight of his obsessive precision. But he knew that choosing the right star was as important as choosing the right instrument. If you want to see a parallax wobble, you want a star that is likely to be nearby, because nearby means larger apparent shift. The best clue to nearness available at the time was something called proper motion, the slow drift of a star across the sky over many years. Most stars hardly budge, which is why constellations hold their patterns over human history. A few, though, creep noticeably even over a lifetime. Just like closer cars on a highway seem to zip across your field of view faster than distant ones, nearby stars tend to have bigger proper motions for typical space speeds. Bessel picked a faint, unremarkable star in Cygnus called 61 Cygni, famous not for its brightness but for its unusually large proper motion. He also chose a specialized tool for the job, the heliometer. At first glance, it looked like just another refracting telescope, but its front lens was literally cut into two halves. One half could slide sideways relative to the other, which meant the instrument could produce two separate images of the same star field. By adjusting how far you slid the half lens and reading a scale, you could measure tiny angular separations with extraordinary precision. Under good conditions, Bessel could get down to about 1/10 of an arcsecond, right in the territory parallax lived. Even with such an instrument, you still cannot trust a single star's position on its own, because your entire reference frame might be drifting. Buildings settle, mountings flex. The question is not where the star is in some absolute sense, but where it is relative to something you can treat as fixed. So Bessel chose several reference stars in the same patch of sky as 61 Cygni, stars he believed were much farther away, and therefore had essentially Z0 measurable parallax. Every clear night he measured the angular distance from 61 Cygni to each reference star again and again. As Earth moved around its orbit, those repeated measurements traced a tiny ellipse. In January 61, Cygni's separation from its reference partners leaned one way. In April it leaned another way. In July it flipped. By October it was back near where it started. Buried inside that loop were several effects all mixed together. There was the star's own proper motion, a steady drift across years. There was stellar aberration, the umbrella in the rain effect discovered by Bradley. There was atmospheric refraction, changing with altitude and weather. And there was, Bessel hoped, a genuine parallax wiggle. The size of that parallax was dwarfed by the corrections he had to apply. Refraction could displace a star by tens of arcseconds when it was low on the horizon, easily 100 times larger than the parallax he was hunting. Aberration could shift positions by about 20 arcseconds. Thermal expansion and mechanical flexure could change readings by fractions of an arcsecond that was still huge compared to the desired signal. Each of these needed a model. Each model needed parameters measured independently. Each parameter came with its own uncertainty. So Bessel did what Bessel did best. He turned his life into a correction factory. For 13 months starting in August 1837, he observed 61 Cygni and its reference stars night after night whenever weather permitted. He logged temperature, pressure, and wind. He checked his scale readings and repeated measurements in different sequences to catch subtle biases. Then, away from the telescope, he ground through the data by hand, stripping out aberration, refraction, proper motion, and every other known effect to see what remained. What remained was small but stubborn. After all the corrections, the star's apparent position still traced a narrow ellipse with a semi-major axis of roughly 0.3136 arcseconds. That number is comically tiny. The width of a period at the end of a printed sentence seen from across a football field subtends a similar angle. Yet from that angle and the known size of Earth's orbit, Bessel could compute the distance. He found that 61 Cygni lay about 10.3 light-years away, or in more raw terms, about 97 trillion kilometers. Modern measurements put 61 Cygni at about 11.4 light-years. Bessel's answer was off by around 10%. For a measurement at the very edge of what his instruments and atmosphere could possibly support, done with no electronics, no digital sensors, no computers, that is astonishing. In one stroke, he had turned the nearest star from a mysterious point on a crystal shell into something with a specific finite distance. If you could drive a car at highway speed in a straight line, it would take you more than 100 million years to get there. This was not simply a technical success, it was a psychological break. For 2,000 years, people had wondered how far away the stars really were and had no measurements to offer, only guesses. Bessel could point to a line of reasoning, a stack of corrections, and a number. Colleagues checked his work and, after some initial caution, accepted it. The crystal sphere was dead. The stars were now scattered through space at knowable distances, however extreme those distances might be. Hidden inside his result was a subtle invitation. The parallax angle he measured was such an awkward quantity for daily use that astronomers began to look for a better way to package it. 0.31 arcseconds is a strange way to speak about a nearby neighbour, but the geometry itself offered a natural reference. If a certain parallax corresponds to some distance, what distance would correspond to a neat parallax of exactly 1 arcsecond? Turn the triangle around. Define that distance as a standard. That thought, which would soon harden into the parsec, grew directly from Bessel's triumph over the impossible angle. In the next part, the story will widen again. Bessel's single star will become 3, then dozens, then hundreds as other observers join in. The numbers will pile up, the scale of the galaxy will balloon, and the human picture of the universe will lurch from tight and compact to huge and mostly empty. Once you have one true distance, it is very hard to stop. Once Bessel had cracked one star, the rest of the sky suddenly looked vulnerable. If 61 Cygni could be pinned down with a specific distance, so could others. Across the world, astronomers who'd been wrestling with parallax for years looked at their notebooks with new energy. The problem was no longer whether stellar parallax was measurable. Bessel had answered that. The new challenge was how far and how fast they could extend this new cosmic ruler. In Cape Town, on the other side of the planet from Königsberg, Thomas Henderson had already been quietly working on the same question. From the Royal Observatory there, he had collected a series of measurements of a bright southern star we now call Alpha Centauri. He saw a shift in its position that looked very much like parallax, but he was cautious to the point of paralysis. The instruments might be off, the atmosphere might be tricking him. He kept delaying publication, always wanting one more check, one more calculation. When news of Bessel's success with 61 Cygni reached him, the psychological dam broke. If one person had managed a reliable parallax, then the method itself was sound. Henderson rushed to finish his analysis and finally published his own result. Alpha Centauri turned out to be even closer than Bessel's star, around 4 and a bit light-years away by modern standards, with a parallax much larger than 61 Cygni's. In a twist of history, Henderson had actually gathered his data years before Bessel pointed his heliometer at Cygnus. By the calendar, he was first, but in science, the one who publishes first usually gets the historical credit. Farther north, at the Dorpat Observatory in what is now Estonia, Friedrich Georg Wilhelm Struve had been labouring over another bright target, Vega. This star is much farther away, so its parallax is smaller and harder to measure. Struve's result was not as precise as Bessel's or Henderson's, but it was good enough to qualify as a genuine detection. That gave the community 3 solid distances to 3 specific stars. For the first time in human history, The universe beyond the solar system was not just a pattern on the dome, it was a set of places with actual numbers. Those numbers were shocking. Alpha Centauri at about 4.5 light-years, 61 Cygni at around 11, Vega much farther, nearer 25, converting them into kilometers produced figures with so many zeros that even hardened mathematicians felt their stomachs drop. Tens of trillions, hundreds of trillions. If the distance from Earth to the Sun was one modest stride, the nearest stars sat hundreds of thousands of strides away. The solar system was no longer the main stage with stars painted just behind it. It was a tiny neighbourhood du Sud at the centre of a vast, sparse forest. As more observatories joined in, distances to dozens and then hundreds of stars accumulated. Each parallax measurement was tedious, fragile work, often based on years of observations, but the pattern that emerged was unmistakable. Most stars were not near at all. The Sun was not sitting in a tight cluster. It was an ordinary star surrounded by emptiness, with neighbours scattered at wildly varying ranges. Some bright stars turned out to be closer than expected. Others, bright because they were truly enormous and luminous, sat far beyond. The sky's flatness dissolved. This new depth perception transformed the way astronomers thought about the Milky Way. Before parallax, some imagined the galaxy as a modest swarm of stars only a little larger than the solar system. The fixed dome encouraged that small-scale picture. After parallax, that stopped making sense. If the nearest star was more than 40 trillion kilometers away, and bright stars like Sirius and Betelgeuse were far beyond that, then the system had to be huge. Astronomers began to talk of the galaxy being millions of times larger than the distance between Earth and the Sun. The comforting, finite shell gave way to a sprawling disk of stars tens of thousands of light-years across. This had a quiet philosophical bite. The Copernican revolution had already knocked Earth out of the centre of the cosmos and made it one planet among several. Parallax now knocked the Sun off its pedestal. It was not a special lantern with a handful of stars for decoration. It was one more star among many, not even particularly bright. The ladder of importance that had run Earth, Sun, stars, crystal sphere, heaven was being sawed apart rung by rung. We were not in the middle of things in size or position. At the same time, the new distances gave astronomers a sense of scale for everything else they were doing. When they studied binary stars like the ones Herschel had discovered, they could use orbital periods and separations together with distance to calculate masses. Knowing that a binary system sat, say, 20 light-years away, and that its angular separation translated into a certain number of astronomical units meant they could apply Newton's gravity and weigh the stars. Suddenly, parallax was not just about bragging rights, it fed directly into stellar physics. The explosion of parallax work also exposed a practical nuisance. Writing that a star was 97 trillion kilometers away every time was unbearable. Even expressing distances in astronomical units meant trotting out numbers like hundreds of thousands. Scientific papers began to drown in long strings of digits. Everyone was doing the same geometric trick with Earth's orbit and the same conversions, but they were talking about the results in clumsy language. It was the kind of repetitive irritation that breeds a new standard. From this irritation, combined with the clean geometry of Bessel's triangle, the idea of a new distance unit emerged almost naturally. Instead of explaining each time that a certain star has a parallax of some messy fraction of an arc-second, and therefore lies such and such distance away, why not define a standard distance directly linked to that angle? If a star had a parallax of exactly 1 arc-second when measured from Earth's orbit, whatever that distance turned out to be could become the unit. That distance is long, about 30 trillion kilometers, but at least it would tie cleanly to the measurement method. By itself, a new unit does not make the universe larger, but giving something a clear name and a simple relationship to data changes how people think with it. As parallax distances accumulated, the old image of a small finite cosmos never recovered. The universe had suddenly got huge, not just in an abstract philosophical way, but in the precise language of angles and baselines and very large numbers. The next step was to formalize that language into something astronomers could use every day without drowning in zeros. That step would give us the Parsec, and with it, a new way to talk about cosmic size. By the time dozens of stellar parallaxes were on the books, astronomers were living inside triangles. Every distance to a star came from the same picture in their heads: Earth on one side of its orbit in January, Earth on the other side in July, and the star at the tip of a very long, very skinny triangle. The base length was known, the angle at the star was measured, and trigonometry did the rest. The method was conceptually simple. What was not simple was the way people talked about the results. Imagine writing paper after paper where every distance has to be described as so many hundreds of thousands of astronomical units, or this many tens of trillions of kilometers. The values looked monstrous on the page. Authors had to repeat the same explanation endlessly. The parallax angle is such and such a fraction of an arc-second, therefore this distance is this gigantic number. The geometry was beautiful, but the language was clumsy. That is exactly the kind of irritation that makes people invent a new unit. To see how that unit was born, we have to zoom in on something tiny. An arc-second. Humans inherited a strange way of carving up circles from ancient Babylonian mathematicians. They like the number 60 because it has many divisors. You can split it into halves, thirds, quarters, fifths, sixths, and so on. Over time, this base 60 habit crystallized into a system where a full circle became 360 degrees, each degree became 60 arc minutes, and each minute became 60 arc seconds. An arc second is 1 part out of 3,600 in a single degree. This breakdown has no deep connection to physics. It is a cultural choice that stuck. Yet it sat quietly underneath every parallax measurement. Angles on the sky were expressed in degrees, minutes, and seconds because that was the shared language of astronomy and navigation. When Bessel said that 61 Cygni had a parallax of about 0.3 arcseconds, he was speaking Babylonian geometry with a 19th century accent. Now combine that angular system with the size of Earth's orbit, draw the standard triangle one more time. The base is 1 astronomical unit, the distance from Earth to the Sun. The angle at the star is the parallax. If the parallax is tiny, the triangle is extremely long and skinny. But the trigonometry still works. You can always solve for the hypotenuse, which is the distance to the star. Somewhere in that community, someone asked a very natural question. What would the distance be if the parallax were exactly 1 arcsecond? Whatever that comes out to, let us give it a name. Work through the trig and that distance turns out to be about 30 trillion kilometers. That is so far out of human experience that the raw number hardly matters. What matters is the relationship. A star that shows a parallax of 1 arcsecond sits at 1 unit of distance. A star that shows half an arcsecond sits at 2 units of distance. A parallax of 1/4 arcsecond means 4 units. 1/10 means 10 units. Tiny angle, big distance tied together in a simple inverse. They called that unit the Parsec, a mashup of parallax and arcsecond. It is one of those names that only sounds natural after you have heard it 1,000 times. At first, it must have felt like inside jargon, a private joke in the observatory lunchroom. But the moment you start writing distance equals 1 divided by parallax, expressed in arc seconds, and you decide that the answer is in parsecs, your life gets much easier. Every time you look at a notebook full of parallax values, you can convert them to distances in your head. Suppose you measure a star with a parallax of 0.5 arcseconds. That is 2 parsecs. 0.25 arcseconds, 4 parsecs. 0.05, 20 parsecs. A parallax of 1/100th of an arcsecond means 100 parsecs. The mapping becomes second nature. There is no multiplication by a huge constant to convert to astronomical units, no extra factor to go from astronomical units to kilometers. 1/p is enough. For early astronomers doing everything by hand, that clarity was gold. Notice how arbitrary this all is at a deeper level. 1 arcsecond feels natural only because we happen to slice degrees into 60 and then 60 again. An alien civilization might divide circles into 200 or 500 degrees, and their smallest standard angle might not be what we call a second. If they built a distance unit from their angular system and their orbit size, it would not match our parsec. The parsec is born from human history, not from any fundamental constant of nature. The universe does not care. Almost no star sits at exactly 1 parsec from the Sun. Our nearest neighbour, Proxima Centauri, is about 1.3 parsecs away. Sirius is about 2.6, Vega is around 7 or 8. Bessel's 61 Cygni is a little over 1 parsec. There is no physical change when you cross that range. No new regime of physics switches on. The parsec does not mark a shell in space the way the orbit of Neptune marks the outer region of the classical planets. It is simply the distance that falls out when an angular convenience and an orbital size meet in a triangle. Yet once the parsec was introduced, It spread quickly through professional work because it really did make daily practice smoother. Catalogues could list stellar distances in neat values of a few parsecs or a few tens of parsecs instead of strings of zeros. Absolute magnitudes, which measure how bright a star would be if moved to a standard distance, were defined at 10 parsecs. That made the standard neither ridiculously close nor ridiculously far. Formulas relating apparent brightness, true luminosity, and distance became compact when expressed in parsecs. At this stage, the parsec was still a local tool, a way to tame the nearby stellar neighbourhood, but it carried within it the ability to grow. Once you have a basic unit, nothing stops you from stacking metric prefixes on top. Kilo for 1,000 parsecs, mega for 1,000,000, giga for 1,000,000,000. The same triangle that defined the distance to Bessel's star would later define the scale of the Milky Way and the spacing of galaxy clusters, simply multiplied up with new prefixes. A choice that began as a convenience for navigators of the local sky would quietly become the yardstick for the visible universe. In the next part, we will watch that multiplication happen. The parsec will pick up kilo and mega partners, ride along with Cepheid variables into other galaxies, and become standard even for objects far beyond parallax. At that point, it will no longer be just a clever repackaging of one angle, but the backbone unit and distance ladder reaching almost all the way to the edge of what we can see. At first, the parsec was a local tool. It lived in a sphere of a few dozen nearby stars, a way to describe the distance to Alpha Centauri, or 61 Cygni, without drowning in zeros. But telescopes improved, photographic plates appeared, and suddenly astronomers were no longer satisfied with the Sun's close neighbours. They wanted to know how far away star clusters were, how wide the Milky Way was, and eventually how distant those mysterious spiral nebulae might be. The parsec came along for the ride and had to grow up fast. Think about a typical open star cluster, a loose swarm of young stars hanging together in the disk of the galaxy. With better instruments, astronomers could pick out individual stars in these clusters and measure parallaxes for at least the brighter ones. Very quickly it became clear that many clusters were hundreds or even thousands of parsecs away. Writing 3,000 parsecs over and over again gets old, so astronomers did what they had already done in the metric system. They added prefixes. A kiloparsec is simply 1,000 parsecs. The Milky Way's central region sits roughly 8 kiloparsecs from the Sun. Globular clusters, those dense spherical balls of ancient stars that orbit the galaxy's halo, can be 10 or 15 kiloparsecs out. Whole conversations about galactic structure became easier once people could say that a spiral arm feature lay several kiloparsecs from the centre instead of thousands of parsecs. The unit that began as a clever trick for individual stars quietly became the natural scale bar for mapping our home galaxy. Then the story jumped outward again. Early photographs of the sky showed fuzzy spiral shapes that did not look like ordinary nebulae. Some astronomers argued that these spirals were gas clouds inside the Milky Way. Others suspected that they might be separate island universes, entire star systems far beyond our own. The debate simmered for decades because nobody knew their distances. Without a distance, you cannot tell whether you're looking at a small thing nearby or a huge thing far away. The turning point came when Henrietta Leavitt discovered that specific variable stars, Cepheids, had a tight relationship between their pulsation period and their true luminosity. Measure how fast one pulsates and you know how bright it really is. Compare that intrinsic brightness to how bright it appears and you can infer distance. That discovery gave astronomers a new kind of ladder rung that could reach far beyond simple parallax. For the first time, they had stars that could serve as standard candles in very distant systems. Edwin Hubble took that relationship and pointed one of the largest telescopes of his time at the Andromeda Spiral. On his glass plates, he resolved a handful of individual Cepheid variables. He measured their periods, used Leavitt's relation to get their true luminosities, compared that to their apparent brightness, and found that Andromeda's distance was staggeringly large. Even his underestimated early value, a few hundred kiloparsecs, put it far beyond the edge of the Milky Way. The work pushed the distance to around 780 kiloparsecs, or about 0.8 megaparsecs. Megaparsec simply means 1 million parsecs. Once other galaxies began to reveal their Cepheids, their distances fell naturally into that scale. The Virgo cluster of galaxies sits around 16 megaparsecs away. The Coma cluster is about 100 megaparsecs distant. What had been a handy unit for star positions in the local neighbourhood was now the measuring stick for mapping the great clusters and filaments of galaxies across space. Here is where the parsec entangles itself with one of the most important relations in all of cosmology. Hubble did not see to stop at measuring distances. He also measured how quickly those galaxies were receding using their red shifts. He found that more distant galaxies tended to be moving away faster. Plotting recession speed against distance, expressed in megaparsecs, he saw a roughly straight line. The slope of that line is what we now call the Hubble constant. In its common form, it is written in units of kilometers per second per megaparsec. Every extra megaparsec of distance adds a fixed number of kilometers per second to the recession speed. This choice of units is not an accident. Distances to galaxies came from techniques calibrated in parsecs and expanded to kiloparsecs and megaparsecs. Red shifts gave velocities in kilometers per second. Put those together, and the natural combination is kilometers per second per megaparsec. The expansion rate of the universe, our best guess at how far space itself stretches, is literally defined in terms of the parsec's mega-scaled cousin. Change the underlying distance unit, and every quoted value of the Hubble constant would need to be rewritten. As telescopes looked deeper, the hierarchy continued. Galaxy surveys mapped hundreds of millions of light-years of space and showed that galaxies are not sprinkled randomly but arranged in sheets, filaments, and nodes surrounding great cosmic voids. Distances between major features in this cosmic web are often hundreds of megaparsecs. Push even farther to the edge of the observable universe, and you start talking in gigaparsecs, billions of parsecs, to describe moving distances to the most distant galaxies and the surface of last scattering in the cosmic microwave background. At this point, the parsec had fully escaped its original neighbourhood. Astronomers were using kiloparsecs to describe orbits of stars around the Milky Way, megaparsecs to describe the spacing of galaxies and clusters, and gigaparsecs to describe the size of the observable universe in their chosen coordinate systems. Every major map of structure, from the spiral arms around us to the largest three-dimensional surveys of galaxies, was plotted with axes in parsec-based units. What began as a convenience for one measurement trick became the spine of the cosmic atlas. Yet the definition never changed at its core. 1 parsec remained the distance at which one astronomical unit subtends 1 arc second. The only difference was that the community kept bolting metric prefixes on top as their observational reach grew. The same triangle that had given Bessel the distance to one faint star in Cygnus was now, conceptually, the triangle behind statements like the Virgo cluster is 16 megaparsecs away, or the observable universe has a radius of about 14 gigaparsecs in co-moving coordinates. If you step back, it is a little absurd. The largest structures we know, patterns of clusters and voids spanning billions of light years, are labelled using a unit rooted in ancient Babylonian angle divisions and 19th century trigonometry. But that is how scientific standards often evolve. A clever local hack proves useful, gets copied, accrues layers of meaning and quietly grows into a foundation stone. The parsec rode that path from the star next door all the way out to the edge of what our telescopes can see. In the next part, we will climb the distance ladder more methodically. We will see how parallax, Cepheid variables, supernovae, and other techniques lock together into a chain that runs from a few parsecs to billions, and how nearly every link in that chain is labelled in this same odd unit that began as a way to make arithmetic easier on tired 19th century eyes. By now we have one solid rung on our cosmic ruler. Parallax gives distances to nearby stars in parsecs by pure geometry. That alone would already be a triumph, but it is nowhere near enough. Parallax fades into noise after a few hundred parsecs for ordinary stars, even with excellent instruments on the ground. The universe does not end there. If we want to reach the far side of the Milky Way, other galaxies, and finally the large-scale structure of the cosmos, we need a whole chain of methods. Astronomers call this chain the cosmic distance ladder. The ladder starts with parallax because that is the only method that does not care what a star is made of or how it shines. It is simple triangulation. Measure the tiny shift against distant background stars as Earth orbits, convert angle into distance, and you are done. This geometric base is crucial. Everything else that comes later leans on it one way or another. If parallax distances were badly wrong, the entire ladder above would wobble. The next step is something confusingly named spectroscopic parallax, which has nothing to do with actual parallax. It would be better called spectroscopic distance estimation, but traditions are stubborn. Here the idea is to take a star's spectrum, spread out its light into a rainbow with absorption lines, and read from those lines what kind of star it is. Hot massive stars with thin atmospheres show different line patterns than cool, low-mass stars. Once you know the type, you can thus place the star on the Hartree-Sprung-Russell diagram, that famous plot of temperature versus luminosity. Over many decades, astronomers have filled this diagram using stars whose distances are already known from parallax. From that calibration they know, for example, that a main sequence star of a particular spectral type has a certain true power output. Compare this intrinsic brightness to how bright the star appears in the sky, and you can infer its distance. It is basically using stars themselves as light bulbs with known wattages. Spectroscopic parallax works out to a few tens of thousands of parsecs for individual stars, enough to probe much of the Milky Way. It is not as clean as geometric parallax. It depends on stellar models, on classifying spectra correctly, and on the assumption that stars of the same type really do have similar luminosities. Dust can dim light and cause extra uncertainty, but when you average over many stars, patterns emerge. This rung lets astronomers map clusters, trace spiral arms, and sketch the structure of our galaxy in kiloparsecs. The next rung is where Henrietta Leavitt's work changes everything. Her discovery that Cepheid variable stars have a tight relation between their pulsation periods and their true brightness gives astronomy its first robust standard candles. A standard candle is any object whose intrinsic luminosity you can know without already knowing its distance. Candles are useful because brightness drops in a predictable way with distance. If you know how bright something truly is, and you measure how bright it looks, the ratio tells you how far away it must be. For Cepheids, the process goes like this. You watch a star over weeks and record how its brightness goes up and down. You measure the period of this rhythm. From the calibrated period luminosity relation, built using parallax distances to nearby Cepheids, you infer the star's true luminosity. Then you compare that to the observed brightness and solve the inverse square relation. If a Cepheid appears 4 times dimmer than one of the same type at a known distance, it must be twice as far away. All of this is done in parsecs because that is how the calibration was built. Cepheids are powerful because they are intrinsically bright, thousands of times more luminous than the Sun. With big telescopes, you can detect individual Cepheids in other galaxies millions of parsecs away. Suddenly the ladder leaps beyond the Milky Way. Edwin Hubble used exactly this trick on Cepheids in Andromeda to prove it is another galaxy entirely, not a cloud within our own. Modern astronomers still use Cepheids to nail down distances to relatively nearby galaxies and to calibrate even more extreme methods. Above Cepheids on the ladder sit Type 1 supernovae. These are white dwarf stars in binary systems that have quietly stolen mass from their companions until they cross a critical threshold and ignite in a runaway thermonuclear explosion. For subtle reasons rooted in the physics of degenerate matter, they tend to blow up at roughly the same mass and therefore reach very similar peak luminosities. They can be seen across billions of parsecs, briefly outshining the galaxies that host them. Again, calibration is everything. Nearby Type 1 supernovae in galaxies whose distances are already known from Cepheids let astronomers pin down the typical peak brightness. With that in hand, each new explosion in a faraway galaxy becomes a marker on the ladder. You measure how bright it appears at maximum, infer its distance in megaparsecs, and pair that with its redshift to study the expansion of the universe. This is the rung that revealed in the 1990s that cosmic expansion is accelerating, forcing us to introduce dark energy into our models. From there, the ladder grows more intricate. Methods like surface brightness fluctuations, which use the graininess of unresolved stars in galaxies, baryon acoustic oscillations in the large-scale clustering of galaxies, and gravitational lensing all add extra checks at different distance ranges. Each method has its own quirks and sources of error. None is perfect, but the power of the ladder comes from overlap and redundancy. Where 2 methods apply to the same objects, they can be compared. If they agree, confidence rises. If they disagree, something is wrong with the assumptions. The shadow side of this elegant structure is that uncertainties also stack. A small error in parallax distances to nearby Cepheids becomes a small error in the period luminosity relation. That becomes a slightly larger error in galaxy distances derived from those Cepheids. That propagates to supernova distances in those galaxies, and onward to measurements of the Hubble constant. When cosmologists argue about whether the expansion rate is 67 or 73 km per second per megaparsec, they are partly arguing about tiny missteps in the lower rungs of this ladder. Throughout all of this, the parsec quietly holds the whole thing together, Parallax produces parsecs directly. Spectroscopic distances are expressed in parsecs because the Hartz-Sprung-Russell diagram is calibrated that way. Cepheid relations are formulated in terms of absolute magnitudes defined at 10 parsecs. Supernova analyses convert their brightnesses into distances in megaparsecs because that is the natural scale for galaxies. The Hubble constant is written with megaparsecs in the denominator. You could, in principle, redo the entire structure in light years or meters. In practice, rewriting every catalogue, every formula, and every piece of software would be a nightmare. So when astronomers speak casually about a galaxy being 30 megaparsecs away or a star cluster sitting at 5 kiloparsecs from the galactic centre, they're invoking the whole ladder, whether they think about it or not. Those numbers are not direct measurements from a single experiment, but the endpoints of a chain stretching back to Bessel's heliometer and the tiny arcs he teased out of nightly observations. The distance ladder is one of the great conceptual achievements of modern science. It turns flickers of light on glass plates and subtle shifts of spectral lines into a three-dimensional map of the cosmos. In the next part, we'll bring the story into the present with Gaia, the satellite that took the lowest rung of this ladder and exploded it into more than 1 billion precise distances. What had once been a narrow staircase of carefully chosen objects became, almost overnight, a vast mesh of measurements, all calculated in parsecs, that reshaped our picture of the Milky Way and locked this odd unit even more firmly into the foundations of astronomy. For most of the history we have been talking about, parallax was a heroic sport. One observer, one telescope, a few carefully chosen stars, and months or years of staring and hand calculation. The distances that came out of that effort were precious because each one consumed so much human time. Then in the early 21st century, astronomy did what humans always do when something matters. It tried to automate and industrialize the process. The result was a satellite called Gaia, and it turned stellar parallax from a fragile art into a mass production line. Gaia was launched by the European Space Agency in 2013 with an almost outrageous goal: measure the positions and distances of more than 1 billion stars in the Milky Way with a precision previous generations could barely imagine. That is roughly 1% of all the stars in our galaxy. 1 billion might not sound like much when you hear that there are hundreds of billions of stars in total, but for astronomy it was a revolution. Before Gaia, catalogues with 100,000 decent parallaxes were a big deal. After Gaia, 100,000 stars is a tiny subset. The satellite carries 2 telescopes mounted at a fixed angle to each other on a single spinning platform. As Gaia slowly rotates and orbits the Sun along with Earth, the 2 fields of view sweep across the sky in a carefully designed scanning pattern. Every time a star drifts across the detectors, Gaia records its position with exquisite precision. Over the course of years, each star is observed again and again from slightly different points in Earth's orbit, and those repeated snapshots contain within them the parallax wobbles and proper motions needed to reconstruct three-dimensional positions. The key leap is in angular precision. Earlier ground-based work could sometimes reach milli-arc-second accuracy, thousandths of an arc-second in the best cases. Gaia pushes into the realm of micro-arc-seconds, millionths of an arc-second, at least for the brighter stars. To give your intuition something to hold, that is like measuring the apparent width of a human hair from hundreds of kilometers away, or the size of a small coin seen from the moon. At that level, almost every nearby star that once looked fixed begins to trace a tiny ellipse over the mission lifetime. All of this raw measurement would be useless without an equally ambitious data processing system on the ground. Gaia continuously beams down a fire hose of numbers. Engineers and scientists built complex software pipelines to turn those numbers into positions, parallaxes, proper motions, and brightness measurements in different colors. At every step they have to correct for subtle effects. The satellite flexes slightly as it warms and cools. Its orbit around the Sun and the gravitational pull of planets shift its vantage point. Relativistic bending of light by the Sun changes apparent star positions by amounts bigger than many of the parallax signals themselves. When the first major Gaia data releases arrived, the impact hit almost every corner of astronomy at once. Suddenly researchers could pull precise distances in parsecs for millions of stars with a simple database query. They could map the spiral structure of the Milky Way using real three-dimensional positions instead of guessing from brightness alone. They could trace the motions of stars to see streams from ancient dwarf galaxies that were torn apart and absorbed by the Milky Way long ago. They could refine the properties of exoplanet host stars which meant tightening estimates of planet sizes and densities. Hertzsprung-Russell diagrams, which once were painstaking constructions based on a few thousand stars, suddenly bloomed with hundreds of thousands of points. Patterns that had been hints became sharp sequences. Rare evolutionary phases that were once represented by a handful of examples now appeared with enough numbers to analyze statistically. Theoretical models of how stars age and change could be tested against this wealth of data, and any mismatch between model and Gaia measurements stood out. The ladder between observed brightness, distance into parsecs, and true luminosity tightened dramatically. Every line of Gaia's main catalogue speaks parsec. The mission's fundamental measurement is parallax in arc-seconds, or more often in milli or micro-arc-seconds. Converting those to distance in parsecs is as direct as taking one divided by the parallax, after accounting for some statistical subtleties when parallaxes are small and noisy. All of the higher-level products that Gaia enables, from maps of the galactic disk to reconstructions of the Milky Way's merger history, inherit that choice. The internal language of the mission is geometry that Bessel would recognize, just done on an almost absurd scale. This has practical consequences for the rest of the field. Because Gaia is now the reference for stellar distances, any project that cares about stars has to speak its language. If you want to calibrate Cepheid variables more accurately, you take Cepheids with good Gaia parallaxes and express their distances in parsecs. If you want to refine the period luminosity relation, you do it in parsec-based units. Those improved standard candles then feed into better distances for nearby galaxies, which in turn refine the Hubble constant and other cosmological parameters. The ripples spread outward, all starting from those parallax-based parsecs. Economically and socially, Gaia locks the parsec even more firmly into place. The mission took decades of planning and development and cost on the order of $1 billion in currency. Hundreds of scientists and engineers built their careers on designing its instruments and data systems. Entire research programs are now organized around mining Gaia's catalogues. The software ecosystems developed for this work, from database structures to analysis libraries, assume parsec units as a default. When that much infrastructure exists, switching distance units would be like tearing up all the railway lines in a country to change their width. Not impossible, but hardly attractive. Gaia also made something more philosophical visible. Up to a point, you can think of parallax as a cute idea in textbooks, a diagram drawn on a board. With a billion-star survey, it becomes a palpable property of the sky. Every dot in a Gaia map has not just a position and colour, but a measured depth. The Milky Way's disk that once looked like a hazy streak now resolves into a warped, flared structure. Streams of stars trace ghostly arcs that mark where smaller galaxies once plunged through. All of these vistas would be blurry guesses without distances, and almost all those distances arrive wearing parsec labels. In a sense, Gaia marks the moment when the parallax-based definition of distance becomes non-negotiable for professional work. You can still tell stories in light years for the public, and you should. But under the hood, the database that holds our best knowledge of where stars actually are uses the unit tied directly to the arc-second geometry. The weird human-made choice that birthed the parsec has been reinforced by some of the most sophisticated hardware and software our species has ever pointed at the sky. In the next part, we will complicate the picture again. Once you begin to use Gaia's parsec distances to look far outward, you run straight into general relativity and cosmic expansion. Beyond the nearest neighbourhood, even the idea of distance itself starts to fracture into different definitions. The parsec still appears everywhere, but the path from observation to that neat number in a catalogue involves curved space-time, expanding grids, and more than one way to answer the question, how far away is that? So far, our triangles have lived in a friendly world. Space was flat, light rays were straight, and if you said something was 10 parsecs away, that felt like a single, well-defined idea. General relativity takes that simplicity, smiles politely, and flips the table. Once you admit that mass bends space-time and that the universe itself is expanding, even the basic question, how far away is that galaxy, starts to split into multiple answers. The parsec keeps showing up in all of them, but the road from observation to number gets much twistier. Einstein's general relativity says that mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. Light no longer travels along straight lines in the Euclidean sense. It follows the straightest possible paths inside a curved geometry, the routes called geodesics. Around massive things like galaxies and clusters, Those geodesics bend. Light from a distant quasar passing close to a heavy foreground galaxy can be deflected so much that we see multiple images of the same object or smeared arcs and rings of light wrapped around the lens. These gravitational lenses are stunning to look at, but they also deliver a sharp message. Our simple picture of distance as straight-line separation is only an approximation. When light curves on its way to us, the path length is not the same as the naive distance you would draw with a ruler on a flat sheet. At small scales, for stars inside our galaxy and for modest distances in kiloparsecs, curvature effects are tiny, and the usual parsec definition works beautifully. At hundreds of megaparsecs and beyond, ignoring curvature becomes a lie of convenience. Then there is cosmic expansion. Since Hubble, we have known that distant galaxies are not just moving through a static space. Space itself is stretching. Imagine painting a grid on a rubber sheet and then gently pulling the sheet in all directions. Galaxies live at the grid intersections, and as the sheet stretches, their separation grows, even if they are not stepping across the grid. Light emitted from one of those galaxies rides this expanding fabric, and its wavelength gets stretched along the way. That stretching shows up as the redshift we measure in spectra. Here is the annoying part. When you look at a distant galaxy, you do not see it as it is now. You see it as it was when the light left, maybe billions of years ago. During the time the photons have been travelling, the universe has kept expanding, so there are different ways to define the distance to that galaxy, and they give different numbers. In a static universe they would all agree, in an expanding curved one they do not. One useful idea is light travel distance, also called look-back distance. This is the distance that light would have travelled in a straight line at constant speed over the time between emission and detection. If the light has been on the road for 10 billion years, you might say the look-back distance is about 10 billion light-years, or roughly 3 billion parsecs. This matches our intuitive sense of watching the past. It is close to what your gut imagines when you hear that a galaxy's light has been travelling for a certain time. Another idea is proper distance. Imagine that you could magically freeze cosmic expansion at this instant, halt all motion except your own, and then lay down meter sticks or radar pulses from here to the galaxy. Proper distance is the length you would measure in that frozen moment. For nearby galaxies, proper distance, light travel distance, and what you would infer from a simple Hubble law are almost the same. For very distant ones at high redshift, a proper distance can be much larger than the light travel distance, because the universe has continued to expand during the journey. Cosmologists also use comoving distance, which is more abstract but very handy. Go back to the painted rubber sheet. Mark galaxy positions on the grid and then let the sheet stretch. Comoving coordinates move with the flow. In that coordinate system, the galaxies keep the same grid labels even as the physical separation between them grows. Comoving distance between two galaxies is their separation in this expanding grid, with the expansion factored out. It is particularly nice for mapping large-scale structure because it shows the underlying pattern of clustering without the distraction of ongoing growth. For nearby objects, out to perhaps a few tens of megaparsecs, all three distances are nearly identical, and no one worries much about the distinction. For galaxies whose light has been travelling for half the age of the universe, they diverge dramatically. A galaxy we observe with a look-back time of 10 billion years might have a proper distance today of more than 15 or 20 billion light-years, and a different comoving distance again, depending on the exact cosmological model. The phrase "this galaxy is X megaparsecs away" hides a lot of calculation choices. Even worse, the conversion from what we actually measure, which is redshift, to any of these distances depends on our cosmological parameters. To turn a redshift into a comoving or proper distance, you have to assume values for the Hubble constant, the matter density, the dark energy density, and their evolution with time. Change those assumptions and the same redshift corresponds to a different number of megaparsecs. That means distance in parsecs at large scales is not a pure observation. It is observation filtered through a model. Some cosmologists argue that beyond a certain redshift we should stop pretending that distance is the fundamental quantity and just report redshifts directly. Redshift is what the spectrum tells you unambiguously. Distances are model-dependent translations of that one observable. In that view, saying a galaxy is at redshift 1.2 is more honest than saying it is 3 gigaparsecs away, because that number bakes in a particular choice of cosmological recipe. Others push back, pointing out that distances in megaparsecs are easier to visualize and compare, and that experts can always read the fine print to see which distance definition is being used. Either way, the parsec remains in the mix. When a cosmology paper quotes a comoving distance of 4 gigaparsecs to a certain structure, that number comes from integrating over an expanding universe model that itself is calibrated with lower rungs of the distance ladder, all the way down to parallax distances in plane parsecs. When we say the radius of the observable universe in comoving coordinates is about 14 gigaparsecs, that is a very fancy way of saying that if you stretched out all those models and measurements into one line, you would end up with 14 billion times the distance at which one astronomical unit subtends 1 arc-second. So the little triangle that defined the parsec survives the onslaught of curved spacetime and cosmic expansion, but only as part of a larger, more subtle story. At small scales, it is the whole story. At galactic and cosmological scales, it becomes one ingredient in a recipe that also includes redshifts, general relativity, choices about which distance you care about, and an agreed set of cosmological parameters. The number of megaparsecs you read in a paper is not just geometry. It is geometry woven together with theory and convention. In the next part, we will look at another fracture line. Professional astronomers continue to live in parsecs and megaparsecs, while the rest of the world talks about light years. We will explore how that split happened, how it shapes teaching and science communication, and why the unit that makes the most emotional sense lost the battle for the research literature to a unit that is purely a child of arc-seconds and human convenience. If you hang out with astronomers for a while, you notice something strange. In research talks and journal papers, everyone speaks in parsecs and megaparsecs. Then the same people step in front of a camera or talk to a journalist and suddenly everything is in light years. It is like watching someone switch languages mid-sentence. Same galaxy, same distance, different words depending on who is listening. That split did not happen by accident. It grew out of two very different needs, and it shapes how the rest of us think about the size of the universe. Light years win the popularity contest easily. The phrase explains itself. Light is the fastest thing there is. A year is an amount of time every human understands. Put them together and you get a distance that instantly feels huge. When you say a star is 4 light years away, people can picture light racing through space for 4 years just to reach us. When you hear that Andromeda is millions of light years away, you feel the time capsule effect. You are seeing the galaxy as it was when early humans were barely figuring out tools. There is a built-in sense of awe. The parsec does not have that gift. You cannot hear the word and immediately decode it unless you have had the geometry explained. Parallax, arc-second, astronomical unit, triangle. It is an inside joke that escaped the observatory. If you tell a general audience that Andromeda is about 780 kiloparsecs away, you get blank stares. If you say 2.5 billion light years instead, you get wide eyes. The underlying distance is the same, but one unit plugs straight into the imagination while the other bounces off. Popularizers of science figured this out early. When television series and books about the cosmos exploded in the second half of the 20th century, their creators almost always chose light years. They wanted to engage emotion, not train people in professional jargon. A light year tells you not only how far, but how long the light has been on the road. It ties distance to time in a way that makes the universe feel more like a story and less like a spreadsheet. That is perfect for documentaries, museum exhibits, and news articles. Professional astronomers, meanwhile, were living inside that spreadsheet. For them, the prime virtue is not poetry, it is frictionless calculation. Parsec distances drop straight out of parallax measurements. 1 divided by the angle in arc-seconds and you are done. Absolute magnitudes, the standardized measure of intrinsic brightness, are defined at around 10 parsecs. Formulas relating brightness, luminosity, and distance become compact with parsecs in the mix. Software libraries, catalog formats, and simulation codes were all built with parsecs as the default distance unit. By the time light years became common in public-facing material, the research infrastructure around parsecs was already deep. Star catalogs listed distances in parsecs. Models of stellar evolution used parsec-based luminosity scales. The Hubble constant was given in kilometers per second per megaparsec. Every layer of data and theory was glued together with this odd unit. Switching the whole system over to light years would have required rewriting textbooks, refactoring software, reformatting databases, and retraining everyone's intuition. There was no strong reason to pay that price. So 2 parallel languages settled in. Inside the field parsecs, outside light years. When an astronomer writes a paper for a technical journal, they say a galaxy is 30 megaparsecs away. When the same astronomer gives a public talk, they say about 100 million light-years instead. They are not hiding anything. They are performing translation on the fly between their native tongues and a lingua franca. But for students and curious outsiders peeking into the research literature, that translation boundary can feel like a wall. Every split-unit system carries risks of confusion. People who grew up on popular science books think in light years. Then they open a research paper or an online catalogue and see numbers in parsecs and megaparsecs. If they do not know the conversion, the distances feel meaningless. 3 megaparsecs sounds smaller than 30 million light-years, even though they are the same. Without context, the scale is easy to underestimate. Misunderstandings like these are why some astronomers advocate always giving both units whenever work is likely to be read beyond a narrow specialist circle. There is another twist. Light years show up in fiction all the time, but usually as vague signifiers of far away rather than precise units. Some space stories toss around parsec as well, and sometimes they get it wrong, treating parsec as a unit of time rather than distance. That misstep is famous enough that plenty of astronomers have used it as an icebreaker in talks. It is a harmless error in a film script, but it reinforces the sense that parsecs are a kind of nonsense word, disconnected from physical meaning, while light years feel grounded. From the point of view of pure physics, light years are not sacred either. They depend on the same human choices. A year is one orbit Earth around the Sun. Change your home planet or your timekeeping system and your year changes. Light speed is a constant of nature, but the duration you multiply it by is not. Still, the concept links directly to observation. A galaxy 10 billion light-years away is one whose light has been travelling for 10 billion years. That story hook gives light years a natural place in public conversation that parsecs will probably never claim. In practice, the two systems coexist. Databases like exoplanet catalogues often let you display distances in either parsecs or light years. Press releases about new discoveries include both numbers. A statement might say that a planet lies 12 parsecs, roughly 40 light years from Earth. Professionals read the parsecs and think about parallax and absolute magnitude. The public hears the light years and thinks about time and the impossibility of visiting. The same announcement carries two parallel narratives tailored to different ears. The cost of this duality is a bit of extra complexity in teaching and communication. The benefit is that each community gets a unit that fits its mental habits. Astronomers keep the unit that makes their calculations tidy and their historical data compatible. Everyone else gets a unit that plugs directly into human intuition about time and speed. As long as we are honest about the conversion and clear about which unit we are using in which context, the cosmos can survive being measured in two different ways. In the next part, we will dive into the classroom. There, this split between parsecs and light years becomes more than a curiosity. Teachers must decide how much geometric detail to demand from students, how hard to push the triangle behind the parsec, and when to lean on the story power of the light year instead. The choices they make determine who finds the universe inviting and who quietly backs away from the board. Walk into a typical introductory astronomy class and the instructor has a choice to make. Do they drag first-year students through arc seconds, baseline triangles, and the geometric birth of the parsec? Or do they lean on light years and jump straight to black holes and exoplanets? The decision sounds technical, but it is really about who feels invited into the subject. A definition that delights professionals can look like a locked gate to everyone else. The parsec lives right on that line between necessary foundation and unnecessary barrier. To genuinely understand a parsec, you have to juggle several ideas at once. You need at least a passing grip on trigonometry, the way angles and sides relate in a skinny triangle. You need to know what an astronomical unit is and how people measure the distance from Earth to the Sun in the first place. You need to be comfortable with the degree, arc-minute, arc-second mess that we inherited from ancient Babylon. For many students, ticking all of those boxes takes a lot of lecture time and a lot of patience. Now imagine that most of the people in the room are there because they need a science credit, not because they are already in love with the sky. They might be struggling with spatial reasoning. They might not have seen trigonometry for years. If their first exposure to astronomical distance is a diagram of a triangle with Earth at two corners and a star at the top labelled with tiny angles and unfamiliar units, some of them are gone mentally before the story even reaches galaxies. The unit that professionals find elegant becomes a weed that chokes off curiosity. Light years sit there as the easy alternative. You can explain the idea in one sentence without any diagrams. Light moves fast. A year is a long time. The distance light covers in that time is huge. Done. Students instantly grasp that 4 light years is small in cosmic terms and millions of light years is enormous. They latch onto the time travel feeling that comes with looking at distant objects whose light began its journey before humans existed. You have hooked their imagination without requiring them to wrestle with arc seconds. So many instructors split the difference. In the first weeks, they talk in light years. They build a sense of scale using metaphors, shrinking the solar system to the size of a beach ball, turning the Milky Way into a city, and putting Andromeda several cities away. Only later, often in a section on how we know what we know, do they introduce parallax and the Parsec. At that point, a smaller group of students is still committed, ready for the more technical story about how the ladder is built from the ground up. For students who intend to become astronomers, that story is not optional. At some point, you have to understand why distance equals 1 divided by parallax, why absolute magnitude is defined at 10 parsecs, why Hertzsprung-Russell diagrams use those conventions. You have to be able to read a Gaia catalogue entry that says a star has a parallax of a few milli-arc seconds, and translate that into an instinctive feeling for how far away it is in parsecs. This is part of learning the community's language, the same way future physicists learn to think in electron volts, or future chemists learn to think in moles. Upper-level courses reflect this split personality. An introductory class might mention the parsec briefly as an interesting professional unit before returning to light years. A course for majors will dive into the geometry in detail, derive the distance relation, and work problems in parsecs only. Graduate seminars do not bother translating. If you ask how far a certain cluster is, the answer comes back in kiloparsecs, delivered with the assumption that you can immediately place that number in the context of the galactic disk. The unit is no longer a concept to be taught. It has become part of the air. This educational pipeline does more than convey facts. It subtly marks who is inside the profession and who is not. People who can juggle parsecs comfortably have passed through a certain training gauntlet. They have done the problem sets, stared at the triangles, and internalized the weird conversion that makes 3.26 light years equal 1 parsec. That familiarity becomes a kind of badge. When everyone around you speaks in parsecs, switching units feels like betraying the tribe. At the same time, teachers are increasingly aware that every extra layer of jargon pushes some potential scientists away. Students from underrepresented backgrounds, or from schools where advanced math was not well supported, may already be carrying the quiet fear that this subject is not for them. If their first signal from astronomy is that even distance is wrapped in a unit that demands 3 prerequisite topics to decode, some will decide this world is not theirs. The way we teach the parsec, and when we insist on it, ends up shaping who gets to feel at home under the dome. There is a middle path that more educators are starting to explore. You can be honest about the professional unit without insisting that everyone become fluent in it on day one. You can teach parallax conceptually, let students feel the triumph of making stars move through triangulation, and then say that astronomers package the resulting distances in parsecs for convenience, much as cooks measure ingredient weights in grams, while diners talk about how full they feel. You can give the relationship to light years and reassure students that understanding the story matters more than memorizing the unit. In the next part, we will step out of the classroom and into the messy world where astronomy collides with other sciences and with engineering. There, the parsec has to share the stage with meters, kilometers, and seconds, and the stakes of unit confusion are not just hurt feelings, but lost spacecraft and tangled collaborations. Watching how teams navigate those collisions reveals another layer of the parsec story, one where tradition meets very practical consequences. By now, the parsec feels comfortably at home inside astronomy, but the universe does not care about academic departments. Modern space science is a team sport that pulls in physicists, engineers, computer scientists, planetary scientists, climate researchers, and more. Most of those fields live in the world of meters, kilograms, and seconds, the international system of units. When their world collides with the parsec world, you suddenly have 2 languages in the same control room. That is when small slips can turn into very expensive mistakes. Physicists are the most straightforward about it. The equations of mechanics and relativity are naturally written in meters and seconds. If you solve Einstein's field equations for the inspiral of two black holes, your simulation tracks their separation in meters as a function of time in seconds. When you compute the gravitational waves they emit, the strain on spacetime is a dimensionless number, but any distance you infer comes out in meters by default. For a theorist doing that math, the parsec is not a helpful friend. It is an extra conversion, one more step where fingers can slip on a calculator. Engineers building detectors like LIGO and Virgo also think in meters. Their job is to measure changes in the lengths of multi-kilometer arms that are smaller than the width of a proton. The mirrors, lasers, suspensions, and vacuum systems are all specified in standard units. When these detectors pick up a gravitational wave from a distant merger, the analysis pipeline relates the observed waveform to a distance in meters based on how strong the signal is. At that point, the astrophysicists grab that number and almost immediately convert it to megaparsecs so they can compare it to galaxy catalogues. This back and forth shows up in other ways. Suppose LIGO announces a neutron-star merger and gives a rough distance of about 40 megaparsecs. An astronomer turns to a galaxy catalogue, which lists candidate host galaxies in the same region of the sky, along with their redshifts and distances in megaparsecs. Meanwhile, a theorist simulating the event might want that same distance in meters to plug back into energy calculations. The computer systems have to convert numbers both ways, meters to parsecs for sky maps, parsecs back to meters for physical models. Every conversion is conceptually simple, but each one is a door where a wrong factor can slip through. Planetary science has its own tangle. Inside the solar system, distances are often quoted in astronomical units because that matches orbital mechanics nicely. 1 unit from Earth to the Sun, about 1.5 times 10 to the 11 meters, 2 units to Mars at opposition, 30 units to Neptune, and so on. Spacecraft navigation teams, however, must eventually work in kilometers because their trajectory software pushes thrusters and checks positions in concrete metric terms. Mission documents end up filled with both astronomical units and kilometers, sometimes in the same paragraph, plus maybe a passing reference to light minutes when talking to the public about communication delays. This is not just a matter of taste. We have a famous cautionary tale. In 1999, NASA lost the Mars Climate Orbiter when it attempted to enter orbit around Mars. One software module produced thrust data in pound-force seconds, an imperial unit. Another module assumed those numbers were in Newton seconds, the matching metric unit. Nobody caught the mismatch before flight. The result was that the navigation calculations were off by a factor of about 4.5. The spacecraft dipped too low into the Martian atmosphere and was destroyed. More than $300 million and years of work vanished because of a unit conversion error. The Mars Climate Orbiter failure did not involve parsecs at all, but it is the nightmare that hovers in the background whenever different unit systems meet. If you have instruments calibrated in one system and models written in another, you need iron discipline about how numbers travel between them. That means attaching units explicitly to every stored value, not just trusting that everyone knows what a column of distances represents. It means testing interfaces with silly extreme values to catch surprises before they reach space. Humans are creative, but we are not naturally good at mental bookkeeping for mixed unit systems. Astronomy is full of smaller, quieter examples. An exoplanet catalogue might store star distances in parsecs for internal consistency, but display light years by default on its public web interface. A paper about a potential habitable world might quote both numbers to satisfy professional readers and general interest. A climate scientist wanting to compare rates of nearby supernovae to extinction events on Earth might pull supernova distances from an astronomical database and immediately convert them into light years to match geologic timescales in their head. Each merge point is a little puzzle that must be solved correctly. Software can help enormously, but only if people let it. Modern data formats allow units to be stored as metadata attached to each column, so a field is not just a list of numbers, but a list of numbers in parsecs or meters or light years. If every tool in the chain respects that metadata, conversions can be done automatically and consistently. You ask for output in kilometers, and the system quietly translates the underlying parsecs for you. But if someone hard codes an assumption, or strips units away for speed, or copies numbers into a spreadsheet without their labels, that safety net disappears. The parsec adds one more twist because it is not part of the official international system. Meter, kilogram, second, ampere, Kelvin, mole, candela. These all sit inside a carefully maintained framework with defined conversion rules. The Parsec lives in a parallel world maintained by the astronomical community. When astronomers collaborate with other fields, they have to bridge those two frameworks. Sometimes that is as simple as agreeing that all shared data will be expressed in meters, even if the astronomy side converts back to parsecs internally. Other times it means teaching colleagues just enough parsec lore that they can read astrophysical plots without getting lost. As astronomy becomes more interdisciplinary, with projects that touch everything from planetary climate to biology to high-energy physics, the social friction of this extra unit becomes more visible. A geophysicist studying how cosmic rays might influence atmospheric chemistry should not have to learn parsecs to use supernova catalogues. A data scientist building machine learning tools for sky surveys should not have to guess whether a distance column is in kiloparsecs or light years. Each extra layer of inside language raises the barrier to entry just a little, and that affects who shows up at the table. The obvious way forward is not to abolish the parsec overnight, but to surround it with smarter tools. Let astronomers keep their natural unit where it serves them, but make sure every database, every file format, and every analysis library understands units as first-class information. Then a gravitational wave astronomer, a spacecraft engineer, and a planetary scientist can all look at the same event and each see distances in the units that make sense for their own work, without anyone retyping conversion factors by hand. The parsec can stay what it has always been, a convenient package for arc-second geometry, while its rough edges get sanded down by good software design. In the next part, we will zoom out one last time and look at the social side of all this. We will see how institutions, traditions, and collective habits have locked the parsec into place, why change it is hard even when alternatives seem cleaner, and how the future might belong less to any one unit and more to flexible systems that translate effortlessly between them. At that point, the parsec will look less like a mysterious length and more like what it really is, a case study in how human choices harden into scientific standards. Standards in science like to pretend they are neutral products of reason. In reality, they are closer to folklore that got written into software. The parsec is a perfect example. No council of wise astronomers sat down and voted that this would be the eternal unit of cosmic distance. It bubbled up from Bessel's geometry, spread because it was handy, and then slowly froze into place as generations of people built their work on top of it. Once enough code, catalogues, and curators were tied to parsecs, changing the unit stopped being a technical question and became a social one. Think about all the layers that lean on this one choice. Parallax distances from Gaia, spectroscopic distances, Cepheid calibrations, supernova surveys, galaxy catalogues, cosmological simulations, teaching materials, and conference talks. Every one of those layers assumes that when you say 10, you mean 10 parsecs, or 10 kiloparsecs, or 10 megaparsecs. If you tried to flip the whole field to light years or meters, you would not just edit a definition. You would have to crawl through millions of lines of code, adjust every database schema, rewrite textbooks, and retrain everyone's intuition. That's a massive coordination problem. Scientists are humans in a hurry. They care deeply about getting the physics right. But they also have papers to finish, students to advise, and telescope time to justify. Rebuilding an entire unit system offers almost no scientific payoff. The stars do not move closer if you switch from parsecs to meters. Hubble's law does not become more accurate because the denominator of the constant use is light years. So any proposal to abandon parsecs runs straight into the question, what problem are we actually solving? If the answer is mostly aesthetic, it dies into the corridor before anyone reaches a committee room. Institutions reinforce this inertia. The International Astronomical Union has issued careful definitions tying the parsec to the astronomical unit and the speed of light. Journals have style guides that assume parsecs. Large missions like Gaia, the Vera Rubin Observatory Survey, and future telescopes such as the Extremely Large Telescope and the Roman Space Telescope all design their data products around parsec-based distances. Funding agencies evaluate proposals written in this language. Students are examined on it. When that many institutions quietly align around a convention, the convention becomes invisible background rather than a visible choice. There is also a softer social pressure. Shared jargon binds a community together. When you stand up at a conference and say that a cluster is 10 kiloparsecs from the galactic center, you are signaling that you belong, that you have been trained in the same way as everyone else. If you stand up and insist on using only light years, you mark yourself as an outsider or a newcomer who does not yet speak the dialect. Nobody will throw you out of the room, but you will feel gentle nudges back toward the standard. That is how human groups maintain coherence without ever talking about it. At the same time, the world outside astronomy keeps tugging in the opposite direction. Popular science works in light years. Interdisciplinary projects bring in people who live in meters and seconds. Open data movements push for archives that anyone can use without learning specialist units first. If a climate scientist wants to look at supernova rates, they do not want to stop and translate megaparsecs in their head. If a data scientist wants to mine galaxy surveys, they would like the software to hide as much unit hassle as possible. All of that pushes toward more flexible, transparent handling of units. The most realistic future is not a triumphant overthrow of the parsec, but a quiet dissolving of its sharp edges. Instead of one true unit, we get smarter systems that treat units as tags rather than identity. Databases already know whether a distance column is stored in parsecs, light years, or meters. Future tools will let each user choose how to see those numbers. An astronomer building a Hertzsprung-Russell diagram might get parsecs by default. A planetary scientist browsing the same data might see astronomical units or kilometers. A science communicator might see light years ready for a press release. Machine-readable metadata makes that kind of shape-shifting straightforward. Once every value carries its unit along as part of its identity, software can convert on demand with high precision and no human finger trouble. That is very different from the old world where someone mailed you a table with a bare column of numbers and you had to read the caption to guess what they meant. In that older world, the safest path was to demand one standard unit everywhere, which is how parsecs got so entrenched. In a world of rich metadata, we can afford to be more relaxed. There is also the fun question of how any of this would look if we ever talk to someone who is not from Earth. A civilization around another star will not measure angles in degrees divided into 60 arc minutes and 60 arc seconds. They will not have an astronomical unit based on Earth's orbit. They might very reasonably think in units tied to fundamental constants or in pure dimensionless combinations. If we ever exchange information about cosmic distances, parsecs will be our local accent, not a universal truth. We will probably define distance using the speed of light and some multiple of a standard time, then both sides can translate into their own home units. So the parsec becomes what it perhaps always was, a historical quirk that turned out to be extremely useful. Its future is not secured by any deep law of nature, but by the weight of accumulated practice and the fact that changing it would bring more pain than benefit. Yet the rise of better software and more open data means that this quirk will matter less to people outside the core of astronomy. They will talk in light years or meters or whatever their own communities prefer and let translation happen beneath the surface. In the final part, we will step all the way back and look at the parsec as a mirror, a tiny piece of scientific vocabulary that reveals how arbitrary choices, social habits, and technical constraints braid together into standards that feel inevitable. By the time we are done, the strange unit that started as a trick for measuring one faint star will have turned into a case study in how human knowledge hardens, shifts, and occasionally remembers that it could have been otherwise. Stand back from the details for a moment and look at what we have really been talking about. On the surface, this has been a story about a distance unit with a slightly silly name, born from a triangle and a tiny angle. Underneath it is a story about how humans decide what counts as normal, how choices become habits, and how habits become invisible rules. The parsec is not just a length, it is a fossil of decisions made by ancient sky watchers, 19th century observers, and modern mission designers, all layered on top of each other until they feel inevitable. Think about the chain. Babylonian astronomers decide to slice circles into 360 degrees because 60 is a friendly number to divide. Centuries pass. Astronomers and navigators keep degrees, minutes, and seconds because everyone else is already using them. Bessel takes that inherited angular system, combines it with Earth's orbit, and defines distances from a measurement that seemed almost impossible at the time. Later generations notice that one particular angle in that system, 1 arc second, makes the arithmetic neat. They name the resulting distance the parsec and move on. None of this was forced by nature. You could imagine an alternative universe where someone chose a different baseline or a different convenient angle, and a different unit now fills research papers. The physics would not change. Stars would still fuse hydrogen, galaxies would still collide, the universe would still expand, but the numbers printed under plots at conferences would be different. Scientists would be equally sure that their way of writing distances was the natural one, That is the quiet trick of standards. Once they are entrenched, they do an excellent job of hiding the fact that they could have been otherwise. The Parsec shows both sides of this. On one side, it really is ingenious. It takes a simple geometric relation and packages it into a unit that drops straight out of parallax measurements. It makes distance equal to 1 divided by angle in a way that people can do in their heads while staring at observational logs. It keeps formulas for brightness and luminosity tidy. For working astronomers who spent decades before calculators and computers, that kind of simplicity mattered. The unit earned its keep. On the other side, it is obviously arbitrary. The choice of arc-second ties back to a base 60 system from long-gone cultures. The factor that turns parsecs into kilometers is a giant mess of digits. No physical law picks out this distance as special, and yet the unit persists, not because it is uniquely wise, but because changing it would cost effort with very little reward. Once Gaia, Rubin, and a century of catalogues are all speaking Parsec, the easiest thing to do is to speak Parsec too. Convenience hardens into tradition, and tradition feels like truth. You can see similar patterns everywhere. Keyboard layouts were set in an age of mechanical type bars and have barely budged, even though other arrangements might be faster for modern fingers. Railway track widths follow decisions made for early trains that still shape how we build high-speed lines. Time zones follow political borders more than they follow the sun. In each case, a mixture of technical constraint, historical accident, and social inertia produced a standard that then became very hard to dislodge. The Parsec simply plays that game on a cosmic stage. There is a temptation to feel disappointed by this. We like to imagine science standing outside of human messiness, operating on pure logic while everything else argues over conventions. Seeing that something as basic as how far away a star is gets filtered through human history can feel like a loss of purity, but there is another way to read it. The fact that science works this way and still produces reliable knowledge is part of its strength. It does not require perfect beings using perfect units. It only requires communities that check each other, compare methods, and slowly converge on systems that are good enough. The Parsec sits right at that balance point. It is good enough and then some. It lets astronomers talk to each other efficiently and build the distance ladder that stretches from Earth to the edge of the observable universe. At the same time, the gap between parsecs in the literature and light years in public conversation keeps reminding us that there is no single sacred language of the cosmos. What matters is that you know which language you're using and how to translate. 4 light years and 1.3 parsecs tell the same story about Proxima Centauri. 30 megaparsecs and roughly 100 million light years tell the same story about a far-off galaxy cluster. If there is a practical lesson here for anyone who cares about science, it is this. Whenever you see a number in a headline or a plot, ask quietly in your mind what choices stand behind it. What unit is being used and why? What assumptions were needed to turn raw observations into that particular figure? None of this undermines the result. It just turns it from a magic answer into a human achievement. A chain of reasoning held together by triangles, telescopes, software, and people who argued over details until they were satisfied. And if there is an emotional lesson, it is gentler. Distance is one of the ways we feel the size of the universe. Whether you measure it in parsecs, light years, or kilometers, the fact remains that beams of light have been crossing unimaginable emptiness for years, centuries, and billions of years before they ever meet your eye. Knowing that the unit we use to describe those journeys was born from a clever hack by a 19th century observer does not make the journeys less impressive. It makes them more human. Our species took its awkward counting systems and shaky telescopes and turned them into a ruler that spans the sky. So the next time you hear that a new planet has been found 40 light years away, or that a supernova exploded at a distance of 20 megaparsecs, you can translate between those worlds. You can picture the light on its long trek, and you can picture the geometry that lets someone turn tiny motions into a concrete number. You are hearing both the universe speaking in photons and humans answering back in the language of chosen units. The Parsec will probably still be here long after this video is forgotten, buried inside catalogues and code, but you do not have to think of it as an obscure technicality. You can think of it as a reminder. Behind every simple number in science, there is a story about how we decided to count that way. Behind every cosmic distance, there is a triangle, a telescope, and a person who cared enough to measure. In the end, that mix of vast impersonal space and small human choices is what makes the universe feel real.